On October 4th, 1992, an El Al Boeing 747 freighter took off from Schiphol Airport near Amsterdam. It was 5:20 p.m. The three-man crew and one passenger were headed to Tel Aviv to deliver a routine cargo shipment. But the flight turned out to be anything but routine. Shortly after takeoff, the co-pilot sent a distress call to the control tower.
Mayday, mayday, we have an emergency. El Al 1862, do you wish to return to Schiphol? Roger, we have fire on engine number 3. Roger 1862. Schiphol, El Al 1862, we have an emergency. Number 3 and number 4 engine inoperative. Request to 7 for landing.
Only 7 miles into the flight, the pilot turned around and attempted to return to the airport.
His closest runway was the crosswind runway, which was, I believe he had almost 30 knots of wind directly crosswind. And to try to line up the airplane to the runway with 2 engines gone on one side, limited controllability, was almost impossible.
The jet was making its final approach to the runway when the pilot suddenly lost control of the giant 747. The plane plummeted at full speed toward a residential section of Belmamir near Amsterdam.
It was like he just was flying straight into the ground. And he hit right at the apex of the apartment building.
The 747 exploded upon impact, and the 11-story apartment building burst into flames. Nobody on board survived the crash, and 47 people on the ground were instantly killed in their homes as they were going about their daily lives.
The rest of the building was essentially considered unlivable. It was destroyed so badly. The authorities were concerned they might have a structural collapse, so they evacuated all the tenants.
A team from the Netherlands led the accident investigation. They invited a team from Israel and the United States National Transportation Safety Board to join them. This was the second mysterious 747 crash in less than a year. 10 months earlier, a China Airlines jet also lost 2 engines and went down in Taiwan.
When the El Al crash occurred, there were so many similarities to both cases that it ended up speeding up the investigations of both of them.
The NTSB was determined to get to the root of the problem during the El Al investigation.
You take eyewitness reports, you take air traffic control tapes, you take the recorders. We can examine them in detail, either in the field or in the lab. And by process of elimination, you can focus down to the area in which is significant.
The primary suspects in this case were the engines, which had lost power during the flight.
A Boeing 747 has 4 engines. If you're facing forward, the number 1 and 2 engines are on the left side on the left wing, and number 3 and number 4 engines on the right side. So going left to right, there's 1, 2, 3, and 4.
747 engines are mounted to the underside of the wing. They are attached to an engine strut with engine mounts, and the strut is attached to the wing with fuse pins. To prevent wing damage, fuse pins are designed to break away cleanly from the wing of the aircraft in the event of a sudden catastrophic engine failure.
There were several eyewitnesses saw pieces coming off the airplane as it flew over the water and as it was circling around to try and get to the airport.
While scouring the bottom of Lake IJsselmeer, investigators found all of engine number 4 and part of engine number 3.
Finding the engine in the water was a significant piece of evidence because it showed us the strut mounting, how it had broken. And of course, this was kind of the key.
As they inspected the engine mountings, they began to suspect that the tragedy had been caused by a single fuse pin that supported engine number 3.
We found one fuse pin had a fatigue fracture. It can start from a small pit from corrosion or a scratch. And fatigue is kind of like if you want to break a piece of metal, you bend it back and forth, and finally it breaks. That's a fatigue fracture. And this will happen even in the strongest airplane material.
Over the years, moisture in the air had caused a tiny corrosion pit of rust to form in the pin. It was just a matter of time before the fuse pin cracked and then broke apart completely.
When one lets go in flight like this, it allowed the engine to rotate, and of course that then overloaded the other fuses, and that caused the separation of number 3. As it came loose, it came down the leading edge of the wing and was tearing up pieces of the leading edge as it went along. And as it reached where number 4 is, it was out in front of number 4, and essentially the airplane flew into the number 3 engine.
That contact caused the damage or enough load to tear off the number 4 engine.
Losing power in 2 engines does not necessarily spell doom for an aircraft.
Airplanes are certified by the Federal Aviation Administration to fly with 50% of your engines. In this case, you have 4 engines, so you should be able to fly with 2 of the engines. But unfortunately, in this case, you have a situation where both of the engines were on, as we mentioned, were the number 3 and number 4 engine, and they were on the same side of the airplane.
If you put a lot of power on one side of the airplane, it tends to want to roll the airplane. And if you can't stop the roll, we thought maybe this was one of the reasons why he lost control. The added damage to the wing in the El Al incident contributed significantly to the controllability problem, as opposed to just 2 engines inoperative.
A few weeks before the accident, El Al had inspected the fuse pins on the Boeing 747 for corrosion and minor fractures. The tests used to examine the fuse pins were unable to detect the fatigue fracture. Since the crash of the El Al 747, Boeing has improved its testing procedures. By bouncing ultrasound waves off fuse pins or passing eddy currents over them, engineers can detect even the smallest corrosion and fatigue fractures. Fuse pin materials have also been upgraded to prevent corrosion caused by old age.
The other fuse pins were made out of what's called carbon steel, high-strength carbon steel. But we designed one out of stainless steel, which will take care of the corrosion problems. And the design was such that the machining would be a lot simpler and would eliminate possibilities of having machine-type defects during the manufacturing process. And so this is subsequently what came of the accident.
It's shocking to think that so much death and destruction could begin with a little bit of rust. Fortunately, since the El Al disaster in 1992, there have been no other fatalities caused by engines unexpectedly dropping out of the sky. Los Angeles has always been notorious for smog and traffic jams. As air pollution and traffic congestion reached nightmarish proportions in the 1980s, the city was desperate for a solution. And the Los Angeles subway system was born. The underground mass transit system, called the Metro Red Line, was part of a $4.5 billion public transportation project that included a 17-mile dual-tunnel subway system to connect downtown Los Angeles to North Hollywood. 3 major tunneling contractors had formed the SKK venture in 1992 to dig out and construct the twin tunnels of the Hollywood Boulevard and Vermont Avenue legs of the underground system. Excavation continued well into the 1990s. But on June 22, 1995, an infamous and spectacular accident made its way into the Hollywood spotlight and spread doubt about the safety of future tunneling under Los Angeles. At 11 a.m., a depression in the middle of famed Hollywood Boulevard suddenly ruptured and disappeared into one of the subway tunnels below. The shocking incident occurred as construction workers were remining an 80-foot section of the South Tunnel in the Hollywood Boulevard leg of the subway system. A gas line, a sewage line, and a high-pressure water main burst and flooded the chasm. Bystanders watched in awe as a huge crevasse appeared right in the middle of the street. Joe Doyle from the California Occupational Safety and Health Administration was called in to investigate the situation.
The hole was growing right when we first pulled up there. Debris was caving off, the dirt was caving off, pavement, asphalt was peeling off of it, Hollywood Boulevard, dropping into the hole. And at the same time, it was filling full of water, which is heavy.
The fallen debris had plugged up the tunnel. But as the water and sewage from the burst lines continued to rise, there was an increased risk that the water would break through the debris and gush through the tunnel. Doyle immediately closed the entrance to the construction site at the Barnsdall shaft, which was 400 feet down the road from the water-filled sinkhole. He then climbed down the shaft to make sure all the workers got out of the tunnel safely.
I said, this thing's going to flush like a toilet. We got to get out of here.
10 minutes later, the water flooded the tunnel below, rushed down the hole, and then shot out into the shaft.
We were immediately up to water to our thighs. We could see these timbers and even steel shooting out of there. It just looked like Armageddon. It was very, very fortunate that no one got killed.
To prevent further cave-ins from devouring the rest of Hollywood Boulevard, SKK needed to plug up the hole fast.
They filled the hole with lean mix, as I called it. Lean mix is sand and gravel, but mixed with very little cement, just enough to give it some strength. It was filled up all the way to the street surface.
When the hole was finally stabilized, the city of Los Angeles repaved Hollywood Boulevard. But it would take a year before engineers figured out how to deal with the disaster below. The initial tunneling of the 3-mile Hollywood Boulevard leg had gone smoothly. To build the foundation for each tunnel, workers erected a temporary support structure out of consecutive concrete rings that would hold up the tunnel walls. These critical rings would become the primary lining of the tunnels. It would take about 8,000 of the 4-foot-wide rings to hold up the 3-mile stretch of the twin tunnels in the Hollywood Red Line. The rings were constructed in the tail of the tunneling machine as it plowed through the ground.
After the ring has been erected, they put in hydraulic expansion device inside the ring and expand the ring outwards so that it gets into contact very tightly, pressing against the earth. After that contact has been achieved, the shape of the ring, which is now expanded, is being locked in place by putting hardwood wedges in the expanded joints. And the ring is just locked in place, pressing against the earth and supporting the earth.
The stability of the primary liners was essential to the structural integrity of the tunnels. Each closed ring had the capacity to hold up 200 tons of earth above a tunnel.
The circle supports itself because it's being subjected to compression. It's sort of like an eggshell when it's complete and you press from the outside with uniform pressure around. An eggshell, even though it's very thin, it is very strong in compression.
After 2 years of digging under Hollywood Boulevard, the initial support structure was finally complete, and construction workers were ready to build the second inner liner inside the primary lining. Except for one problem. The south tunnel had drifted 8 inches out of alignment as the huge tunneling machine dug through the ground.
The alignment of the tunnel is all designed for a certain radius of the rail and speed of the rail for the metro rail cars. And if the rail comes too close to the tunnel wall, then the car would come too close to the wall during operation.
The contractor decided to fix the problem by moving the tunnel wall out 8 inches away from the tracks. 20 essential 4-foot support rings had to be partially dismantled. Workers removed the upper right corner of each ring. Then they dug out the dirt needed to widen the top of the passageway. They replaced the upper corners with expanded steel segments, creating an arch that extended beyond the bottom half of the rings. The process was supposed to be repeated at the bottom of each ring, so that they could reconnect the tops to the bottoms. Overlooking the fact that the soil was weak in this area and could not support itself, the plan to replace the tops of all of the rings first turned out to be a colossal blunder. The disconnected rings could not hold up the 4,000 tons of soil that comprised the 80 feet of earth above them.
The underlying problem was that by removing all the rings at the top first, they essentially took away the closed ring carrying capacity of the liner. There's nothing supporting the ring itself.
After the accident, a new contractor was hired to finish the job. A decision was made to build a rectangular repair shaft around the site of the collapse. The walls of the shaft were formed by pounding steel casings into the ground and then filling them with concrete. The shaft stabilized the site, making it now possible to dig down from street level, excavating the lean mix and debris, and clearing out the site without risking another cave-in. Once all of the old debris was cleared from the inside of the shaft, the workers could rebuild the damaged tunnel. Instead of spending extra time and money to restore the concrete rings, they converted the shaft into a small reinforced rectangular station box, similar to a subway station. The new box section had tunnel openings on both ends to allow entry for the trains.
They just lay the rail across that box and traverse the box. Just like when the subway enters a station, it comes out of a tube and into a box.
Hollywood Boulevard's 3-mile section of the 17-mile Metro Red Line finally went into service in 1999. Approximately 106,500 people ride the 17 miles of the Red Line every day. But the Great Hollywood Boulevard tunnel collapse so traumatized some local politicians that plans for additional subway lines came to a halt. Meanwhile, car pollution and traffic nightmares continue to plague the City of Angels. Disaster lurks in the most unexpected places and often strikes when all is calm and peaceful. It was a quiet evening on December 17, 1976, at the Port of Los Angeles in San Pedro, California. A Liberian oil tanker, the Sansanina, was moored here at berth number 46 after unloading a cargo of 212,000 barrels of Indonesian crude. During the last remaining hours of daylight, her Italian crew refueled the ship and filled its empty cargo tanks with seawater. This is a routine practice called ballasting that would keep the tanker riding low in the water on her voyage back at sea. What happened next would remain forever in the memory of those who were there.
I was located at my station at Fire Station 112 on Terminal Island. About 7:35, somewhere along there in the evening, as I looked out that window, a tremendous pressure wave hit us.
To tell you the truth, I thought somebody dropped a bomb. It sounded just like that. I looked out the window and a big mushroom going up in the air. And I grabbed the fire phone, but it was dead. Everything had been cut off.
We call this a self-announcing alarm. Everybody ran for the boat. We weren't going to wait around to hear any kind of a signal come from the signal office.
The force of the blast could be felt 40 miles away. In response, some 200 firefighters raced to the pier.
The first thing we saw when we arrived on the scene was a large mass of fire involving the wharf to such an extent that you couldn't identify what actually was out there. It appeared to me that there was a large building there on the wharf that was on fire, and yet I knew that there was no building there of that size.
The building Dahlquist saw was a chunk of the 70,000-ton Sansanina. Part of its midsection had blown out of the water and landed in the parking lot. The rest lay submerged at the bottom of the harbor.
There was fire on top of the water, there was fire on the wharf, there was fire on the land where we had this coke and other materials stored. We simply worked all of those areas with our monitors until we were able to extinguish the fire.
Remarkably, most of the 30 men aboard the Sansanina survived, thanks to the efforts of firemen like Walter Ball, who maneuvered his fireboat through the flaming debris to get the Sansanina crew off the ship.
About the first 5, all of them, they wanted to do was go, let's get out of here. They thought it was going to explode again. It was making all kinds of noises in the ship.
At risk to his own life, Ball stayed put as the last of 18 men clambered down from the ship's stern.
Well, I had to get them forward or we were going to sink. And so I got up in the flying bridge, and away we went.
In the end, more than 50 people were injured and 9 people were dead, including 3 men whose bodies were never found. The cause of the blast that claimed their lives and wrought so much destruction was a mystery.
Accidents are generally caused by a series of small items which fall into alignment, and it appeared that's what happened on the Sansanina that day.
The Coast Guard immediately launched an investigation into what caused the 18-year-old ship to explode. They focused on what the Sansanina crew was doing prior to the blast: ballasting.
Well, in a tank, if you start to fill the water, of course the water goes to the bottom of the tank, and what it does is it forces the fumes out the top of the tank. Most hydrocarbon fumes, like gasoline fumes, are heavier than air. So what that means is when they get up, they don't readily dissipate up into the air. It sits there until it's driven off by the wind or something of that nature.
In most circumstances, the fumes would have been carried off by the wind. But on the day of the explosion, there was no wind, and the highly flammable vapor cloud was trapped between the midship deckhouse and the aft castle.
Well, if you have a huge volume of hydrocarbon mixed with air and you ignite this, what you have created in reality is what we call now a fuel-air bomb. And the effect, of course, can be devastating.
What caused the vapor cloud to ignite will perhaps never be known. There were too many potential sources.
Once you have hydrocarbon gas in the right ratio of fuel and air to be ignited, it will find an ignition source sooner or later. Trust me, on an industrial system, there'll be an electric spark, there'll be something being hot, and it doesn't take much energy to kick this off. It isn't just what collects on deck, that's what causes and finds a source of ignition. There were conduction paths of air-fuel mixtures down into the tanks.
The Sansanina had safety and ventilation systems in place to prevent a fire from ever reaching its cargo tanks.
The chief mate was supposed to have some flame screens in place over openings which were venting out onto the deck. The flame screens are intended to prevent any flame from going into the cargo tanks on the ship. That was an industry practice at the time, and appears they were not in place. It also appears from the Coast Guard reports that some of the gas lines which were intended to carry gas vapors away to safe areas may have been rusted.
Had the vents not been so rusted, they might have had a flash fire on deck, but they may not have had the big explosion of the ship. But all these things came together that day wrong, so a number of people died.
In 1977, almost a year after the accident, the Coast Guard completed their investigation and issued a report. Their analysis of what happened had far-reaching effects in the maritime industry. Today, there are significant safety features on tankers to prevent what happened to the Sansanina. Foremost are inert gas systems.
The theory is that by having no oxygen inside the cargo tank, it will not support combustion. If there is insufficient oxygen, there is no possibility of an explosion or fire.
A typical inert gas system involves taking gases from the ship's boilers and feeding them into the cargo tanks. This drives out all the oxygen. Without oxygen, vapors left in the tank are inert and therefore not combustible. Even though inert gas systems were in use in the 1970s, there were no requirements that the Sansanina have one. Today, no supertanker operates without one. In addition, venting systems are more sophisticated, so that hydrocarbon vapors are expelled high above the ship and unlikely to pool on deck. Ballasting is still routine, but modern tankers no longer mix oil and water. Ballast tanks are separate from cargo tanks.
If you look at the major disasters in history, you see in retrospect a sequence of mistakes, each one of which at the time appeared to be innocent and inconsequential, which all combined in a very unfortunate way at the time of the disaster to create a disaster.
It took an 18-year-old ship called the Sansanina and a horrific accident to expose dangers that stalked oil tankers at sea and at rest in quiet harbors. Nearly 100 years ago, this quiet Boston neighborhood called the North End was the scene of one of the most bizarre engineering disasters in U.S. history. A colossal storage tank stood here in what was once a busy commercial and residential area. It was 5 stories tall, 242 feet in circumference, and 90 feet wide. The tank contained 2.3 million gallons of molasses. Without warning, on January 15, 1919, the storage tank ruptured, spewing a thick, dark wave of destruction. 26 million pounds of molasses spilled out at 35 miles per hour. It wasn't just the molasses that wreaked havoc. Rivets and fragments from the tank shot out like shrapnel. One piece crashed into an overhead train trestle, causing it to buckle. The flood claimed 21 lives, injured 150, and caused more than $1 million in damage. It took months to clean up the sticky mess.
The wave smashed into a nearby firehouse and caused the second floor to pancake down onto the first and trapped the firefighters in an 18-inch crawl space. It ended up killing one of the firefighters, George Leahy, who stays alive for between 2 and 3 hours by keeping his head above the molasses until he no longer can do so and he succumbs and he drowns.
At the time, no one was sure what caused the eruption. 4 years earlier, in 1915, a company called United States Industrial Alcohol, or USIA, had built the tank. Molasses was a key ingredient in the company's namesake product.
Molasses is this black, sticky stuff that's left over when you process sugar cane. To make alcohol from molasses, you dilute it with water, you add yeast, you run it through a still, and you've got rum. Industrial alcohol is the same as rum, but it's distilled to a very high proof and as light and flavorless as they can make it.
Industrial alcohol is a solvent or a liquid compound that dissolves other materials. It's also a key ingredient in the manufacture of munitions. World War I was heating up in Europe, and demand for the product was on the rise.
Industrial alcohol would have been used to make explosives for firing shells and for having them blow up on the other end. There were all kinds of military uses for it.
Company treasurer Arthur P. Gell was put in charge of a new Boston terminal where molasses could be offloaded by steamers and transported by rail to a company plant in East Cambridge. It was up to him to build a tank that could store more than 2 million gallons of molasses.
He had no engineering experience, couldn't read plans, couldn't read blueprints, had no technical experience whatsoever. He was basically a finance person, yet he was charged with the construction of this tank. He had to get the tank built, and he had to get the tank built fast.
Gell hired the Hammond Ironworks Company of Boston to manufacture and assemble the tank. They would build the tank using lap joint construction, a method in which one steel band overlapped another. A horizontal band of 18 plates formed the tank's cylindrical shape. The tank's height would be achieved by overlapping 7 of these rows.
Their specifications said they were going to furnish certain size, certain thickness steel bands for the tank, larger at the bottom and then continually smaller to the top.
The specs were not met. It was a rush job. U.S. Industrial Alcohol had to have the tank ready by the end of 1915. A delivery of 700,000 gallons of molasses was on its way from Cuba to Boston.
There's no documentation that they tested the steel or that the rivets were properly installed or any of that stuff. They did check the tank for leakage by running in 6 or 8 inches of water, but that was hardly a test of the tank's strength.
On December 29th, 2 days before the molasses steamer arrived, the tank was finished. But from the start, there were signs of trouble.
It was leaking at the seams near the lower portion of the tank, which would have the extreme pressures on it.
Over the next 3 years, USIA did nothing to seriously address the problem other than to caulk the leaks. By the fall of 1918, there were more pressing matters that the company faced. World War I was ending, and so would their profits. To tide it over, USIA decided to retool its manufacturing plants to produce alcohol for the liquor industries.
It would have been very easy for U.S. industrial alcohol to switch production from industrial alcohol to rum. They just would have had to design a bottle and put a little extra water in it.
But the company only had a small window of opportunity. Prohibition was likely to go into effect in 1920, so USIA had less than a year to get its product out the door.
Some states had already had prohibition for a good number of years, but in general, it took a while to get the enforcement up and running.
In November 1918, USIA ordered one last huge shipment of molasses from Cuba. It arrived January 12, 1919. That day, more than 2 million gallons of molasses were transferred from ship to tank. 3 days later, the pressure inside the tank proved to be too much. The molasses flood sparked one of the first class action lawsuits in the country. But USIA argued that sinister forces were responsible for the disaster.
The cornerstone of U.S. industrial alcohol's defense in the case was that an anarchist had planted a bomb on the molasses tank site and caused the tank to explode.
But that theory was quickly disproved. Most broken windows were below the flood line. In other words, there was no concussive force. However, there was much evidence of shoddy construction.
The tank was built in a substandard way. It was overseen by a person who didn't really know what he was doing. The steel plates that we used to construct the tank were much thinner than originally called for by the plans. Not enough rivets were used in the construction of the tank, and the tank was not tested properly. In fact, it really wasn't tested at all.
A judge ruled against U.S. industrial alcohol, and the company agreed to pay $628,000 to the victims. The molasses flood is more than a strange footnote in Boston history. The event had an enormous impact on the construction industry, paving the way for tougher regulations.
Just about all of the safety standards that we are used to today, the fact that engineers need to stamp their plans and architects need to sign their work, emanated from the Great Boston Molasses Flood.
If that tank were to be built again, they not only would have stamped and sealed drawings and calculations, they'd also have a follow-up construction observation program that showed that they were furnishing what they said they were and that they were installing the rivets properly.
Testing today is also a crucial and standard part of the engineering process. And we owe it all to a strange and deadly disaster involving molasses. In 1977, the Indiana Department of Transportation broke ground on State Road 912, a 15-mile stretch of highway built to attach the Chicago Skyway to Interstate 80, one of America's coast-to-coast highways.
Indiana DOT built this road as a 6-lane highway. It serves as a front door to a major industrial area for steel mills, oil refineries, heavy industry of all kinds. At the time, this project was the largest construction project Indiana DOT had ever built.
The plans for the new highway included the construction of the Klein Avenue Bridge, a 6,260-foot long, 130-foot high concrete box girder bridge to cross over one of Lake Michigan's major shipping canals. The addition of the new bridge would ease traffic congestion on the local lift bridge.
A lift bridge was the only way across the canal right in the heart of this industrial area. When a ship came in, the lift bridge lifted, all traffic was stopped until the ship cleared. One of the purposes of this new bridge was to go over the top of this canal to provide access from the clearance for the boats underneath and not to stop traffic.
Construction of the bridge began in 1980. By 1982, 1/3 of the bridge's sections were in place, and production was on schedule. But on April 15, 1982, as construction workers poured concrete into the roadbed for a 180-foot span of the bridge's on-ramp, disaster struck. The ramp buckled and suddenly collapsed. A few minutes later, another 180-foot section gave way and crumbled to the ground, flipping over a third section, which dangled precariously in the air by frayed cables.
It was just as if a bomb had landed and just everything was exploded and everything was utter chaos, and all you could hear was people screaming.
I was in a state of shock when I arrived at the job and saw the damage and the mass confusion and the debris of concrete and steel twisted on the ground. There were people covered with fresh concrete because they were pouring hundreds of cubic yards of concrete 70 feet in the air, and it fell along with the bridge and trapped people in the concrete during the collapse.
12 people were killed and 18 were seriously injured. It was the worst construction disaster in Indiana's history. As structural engineers from the National Institute of Standards and Technology searched for clues, they began to trace the origins of the collapse all the way to the selection of the construction method.
This project was somewhat unique in that the contractor was allowed to select what kind of bridge he built.
The contractor, Superior Construction, chose to employ the cast-in-place post-tensioned box girder technique.
It's cast at the final position rather than precast, which is a system in which you cast the members in a factory and then ship them to the site and put them in place.
It's a very strong, very light form of construction that has been pioneered, I would say, over the last 30 years.
There was no requirement for the strength of the concrete in the pads, which is a real surprise to us.
The pads were sort of cast as an afterthought. That is, if there was any concrete left over from casting the structure above, that concrete was used in the pads of the succeeding parts of the structure.
When the structural engineers finally removed all of the debris that had buried the critical concrete support pads, they discovered the pads had cracks.
We do not believe that those cracks were a result of impact during collapse because the debris resting on top of the slabs had no indication of a direct impact. So we concluded from that the cracks that we observed in those critical pads were a result of their being overloaded during construction.
To prove the theory, the engineers took core samples of the concrete pads to a lab to be tested.
As a designer, you'd like to have the strength of a structural element be roughly 2 times the load that will be on it. We put the core in a giant press and we apply a compression load on it until it can't support that load anymore. From that compressive strength, we can estimate what the flexural strength of the concrete is, which is the way the slabs supporting the shoring towers would fail. And we use that estimate to calculate the capacity of the entire slab to resist the vertical load.
Tests verified that the concrete pads were only half as strong as they should have been. They could not support the weight of the shoring towers. The weakness of a single pad triggered a chain reaction that caused the whole system to collapse.
We believe that one of the concrete pads cracked, and that led to cracking of another pad. Both pads were now cracked, and this caused the tops of the shoring towers to shift in one direction. This puts a tremendous bending stress on the U-heads, which we know were poorly constructed. That caused the U-heads to break, and as a result, the crossbeam that was supported by those U-heads falls to the ground. Now we have all of the weight of the structure on one side of the shoring towers, and what happened is the shoring towers buckled and the ramp collapsed.
Construction of the Klein Avenue Bridge resumed later in 1982. The National Institute of Standards and Technology and an independent consulting firm offered recommendations for the construction of the new temporary support system. To ensure they met safety criteria, Superior Construction created a separate design plan for the new temporary support structure. Instead of using concrete pads, larger wooden timber footings were constructed to support the tower legs. These footings were bolted together to form a long, solid foundation.
I think the key lesson from this investigation is the design of the temporary support system in construction. It needs to have the same detail of attention and engineering calculation as the final structure that's being built.
The Klein Avenue Bridge was finally completed in late 1983. Over 20,000 vehicles cross this bridge every day. To commemorate those who died in the state's worst ever construction disaster, the Indiana Department of Transportation renamed the 15-mile stretch of State Road 912 in their honor.